Hello again, everybody. This is Dr. Christopher White, and we are now going to go into part 2 of lecture number 4, where we are going to continue looking at rocks, or more specifically, the sedimentary rocks this time round. Alright, so sedimentary rocks. Sedimentary rocks come in 3 distinct types. There are the clastic sedimentary rocks. Those are sedimentary rocks that consist of fragments of rocks or minerals. Then there are the carbonates. They consist of minerals like calcite, dolomite, and aragonite, and they're produced by the recrystallization of biogenic carbonates. That's shells, bits of animal shell like forams, microfossils, corals, but also they consist of carbonate precipitated directly from seawater onto the bodies of organisms. So that's a passive crystallization onto the bodies of organisms. And then we have chemical sedimentary rocks. Those are sedimentary rocks that consist of minerals deposited due to evaporation or directly from ambient or hydrothermal waters. So clastic rocks are composed of clasts, shock horror. So these clasts are from pre-existing rocks. Those rocks could be igneous, metamorphic, or sedimentary, and the clasts are stuck together by a cement or matrix. So sediments form as the result of due to the action of water, wind, ice, and chemical reactions or gravity with exposed rocks on the surface. So sediments are often transported, during which time the shape of the clasts and the composition of the sediment will begin to change. This means that clastic sedimentary rocks are not only described based on their composition, but also how mature they are. The greater the distance the sediment's been transported for, the more mature the sediment is considered to be. So clasts are defined by their size and shape. The simple classification splits clasts into 4 main groups: muds, silts, sands, and gravels. So mud is anything less than 0.004 millimeters, a silt is between 0.004 and 0.062, a sand is between 0.062 and 2 millimeters, and anything greater than 2 millimeters is a gravel. Now this is a very, very coarse classification scheme, and it's not the one we'll be using, but it gives you an idea of what the basic classification scheme is. So just a slight note, when it comes to distinguishing between mud and silt, it's very, very difficult to make that distinction because you can't actually see the crystals with the naked eye. In fact, you can barely see them using a microscope. The only way to really be able to tell the difference between the mud and the silt is to actually take a piece of the rock and to chew it. And once you chew it, you make a little paste, which you put on the tip of your tongue, and you then rub that paste on the roof of your mouth. If you can feel little particles in the paste, then you have silt-sized clasts. If you can't feel particles and the paste feels kind of silky in its kind of texture, then you only have mud-sized particles. So clasts are composed of grains, and grains are usually polymineralic. Essentially, when you have grains that are singular, the rock is often referred to as monomineralic. So if you have a clastic sedimentary rock made up of just one mineral, it's called monomineralic. If you have a sedimentary rock made up of multiple minerals, it's called polymineralic. Not really a particularly difficult concept there. So this is the classification scheme that's used by geologists on a regular basis. So it's called the Wentworth classification, and it's all these values here, all these labels in red. So we're not going to worry about colloids. Those are super small particles that we're not concerned about. So the scale from smallest to coarsest goes clay, silt, very fine sand, medium sand, coarse sand, very coarse sand, very fine gravel, medium gravel, coarse gravel, very coarse gravel, cobble, and boulder. So, not really actually too much of a difference from this classification scheme here. We just have more classifications for sand-sized particles, more classifications for gravel-sized particles, and of course we then have cobbles and boulders added on the end to cover the extremely large clasts that you sometimes get in sedimentary systems. So it's only a slight improvement on the very basic classification scheme. So the first thing we're going to think about is clast sorting. So sedimentary rocks are often described based on their degree of sorting. And there are two main groups. Well-sorted clastic sedimentary rocks have a very tight range of clast sizes, so all the clasts will be approximately the same size. Poorly sorted clastic sedimentary rocks will have a wide range of clast sizes, so you'll end up with lots of different size clasts in your rock. So sorting is the result of three main processes. The first one is the energy of the transporting environment. So high energy environments can transport both large and small clasts. So if you have, a very high energy environment like a landslide or a very, very fast flowing river, well, that has the capacity to transport both small clasts but also very, very large clasts. And so any sediment that forms from that river may well be very poorly sorted. Then there is the duration of transport. Over time, the transporting medium will reduce in energy, causing particles of similar size to be deposited at set locations. So as the river flows downhill, slowly it begins to lose energy. As it loses energy, first it must deposit the gravel size class, then the sand size class, then the silt size class, and then the clay size class. So you'll end up with essentially sediments of the same size being dropped in approximately the same area. That's also going to help you to essentially sort the sediments. And then finally there's abrasion. So over time, the large clasts that are part of the bed load will bang into each other as they move along the bottom of the river. They'll be rolled or they'll bounce along and they'll bump into other clasts in the bottom of the river. And every time they bump into another clast, a little corner will get knocked off the clasts as they bump into each other. And so slowly over time, through the process of abrasion, the knocking together of all these clasts will slowly round them towards a spherical or elliptical shape. So essentially, the longer the transport, essentially the large clasts get steadily broken down to become smaller and smaller clasts. I should point out that when we discuss abrasion, we are not discussing clay and silt size clasts, because they are not part of the bed load. They don't get transported along the bottom of the river. In fact, they are transported in suspension, so they're held actually in the water. That's why if you've ever been to see the Mississippi River is extremely kind of brown in colour, and that's because of all the silt and clay being held in suspension in the river water. If the silt and clay weren't there, the river water would be nice and clear, but as they are there, it looks pretty murky and pretty cloudy, and you can't see the bottom of the river. So let's have a quick comparison between these two sediments or rocks that we see here. So here we have a rock that's very poorly sorted. We can see we have everything from cobble-sized clasts all the way down to kind of sands in between, and probably all the way down to gravels. Okay, so we can tell that whatever's transported this particular sediment must have been quite energetic, because it's transporting both very large clasts and small clasts. We can also tell actually when we look at the clasts themselves, look how they aren't actually all angular, they're actually ever so slightly rounded. So that tells us that the clasts themselves have actually been transported for a little while and they've had some sharp corners knocked off. That's essentially the start of the process of abrasion. Over time, if this clast here was transported for a long period of time, it would steadily get broken down and become smaller and smaller and smaller. Now let's compare that to this sediment over here. Now in this case, this sediment, as you can see, consists mostly of gravel-sized particles. So it's mostly material that's somewhere between about 4 millimeters and about 32 millimeters in size. So, about 0.5 centimeter to 3 centimeters in diameter. So it's relatively well sorted. So you can also see that clay, silt, all the sands, most of the sizes of gravel, cobbles and boulders are absent, they're not present. So this is a relatively well sorted sediment. Most of these clasts are around the same size. Interestingly though, when you look at this particular set of clasts, you'll notice the clasts are actually quite angular, they've got lots of pointy corners. So that's telling us this particular sediment, although it's reasonably well sorted, it hasn't actually been transported that far. So these clasts haven't had an opportunity to bang into each other and knock off their sharp corners yet. So speaking of roundness, the roundness of clasts, here we go. So rounding defines how close a clast is to a perfect sphere or an ellipse. And clasts are often defined in three ways. They are defined as rounded, sub-rounded, or angular. So rounded clasts contain only rounded corners. So they're going to look something like this. No sharp edges. Angular clasts, on the other hand, contain jagged corners with only a minor degree of rounding, so they're going to look something like these clasts here. Then you have the kind of intermediate stage, which is referred to as sub-rounded, and that's where most of the corners are rounded, but occasionally you still get some smoothly angular corners like these clasts here. Now you see there are other subgroups, subangular and variangular, but we're not going to worry about those. If I ask you to describe the class in a sediment, you'll be describing them simply as either rounded, sub-rounded, or angular. So rounding is the result of three variables. First of all, the hardness of the clast. The softer the clast is, the faster it will round. It makes sense, doesn't it? So a hard mineral like quartz will take a lot longer to round than a soft mineral like mica. So then there's the energy of the environment. The more energetic the environment is, the more impacts a clast will have in a set period of time. Okay, so in a slow-flowing river like the Mississippi, essentially, let's say every clast might bang into another clast, every couple of minutes, because it's a much lower energy system. In contrast, a fast-flowing river in the mountains of Colorado, well, those clasts are going to be banging into other clasts, 5 or 10 times every minute, because they're moving so quickly. And so that means in high-energy environments, you'll get lots and lots of impacts, so clasts will begin to round relatively quickly. And then finally, there's the duration of transport. The longer the sediment is transported for, the more opportunities clasts have to bang into each other, and therefore the better rounded the sediment becomes. So over time, clasts, so sands, gravels, cobbles and boulders, will become more rounded the longer they're transported. So this brings us on to clast maturity. So we've already discussed that over time, as a sediment gets transported, it will become 1, better sorted, and 2, more rounded. Now this is referred to as textural maturity. When you look at the texture of the rock and the clasts within it, it allows you to make an estimation of whether the sediment's been transported for a long period of time or a short period of time. There is, however, another type of maturity, and that's chemical maturity. So many minerals are not stable when they come in contact with water, and they'll begin to break down, often forming clay minerals. A classic example is the mineral olivine. It doesn't like being in contact with water. It will react with the water and it will form clay minerals. So what this means is when you have a sediment consisting of a range of minerals, well, the chemically mature minerals will obviously break down relatively quickly, whilst the chemically inert minerals like quartz and feldspar and clay will remain in the sediment. So you'll lose minerals like olivines and micas, pyroxenes and amphiboles. They'll be lost and converted into clay. And you'll retain minerals like quartz, feldspar and clay because they're chemically inert. So this is called chemical maturity. Essentially, the longer a sediment is transported for, the more chemically mature it will become as well. I do apologize for that. That was Rupert, my pug, who was joining in on the conversation. So maturity allows us to infer the transport distance and the processes experienced by a sediment. So a mature rock will have a greater transport distance from the site of which the sediment was formed, and so that's referred to as a distal sedimentary rock. So the sediment's been transported a long distance from the source region. In contrast, a proximal sedimentary rock is a sediment that's been, proximal sedimentary rock is formed from a sediment that's only been transported a short distance from the source region. And we gauge this level of maturity based on both textural maturity and chemical maturity. Okay, so how are clastic rocks actually split up? Well, clastic rocks are split up into the following groups. If the rock is dominated by gravel-sized clasts or larger, it's referred to as either a conglomerate or a breccia. If the rock is dominated by sand-sized clasts with little to no clay or silt, it's defined as a sandstone. If a rock is a mixture of both sand and clay and silt, it's referred to as a Greywackes. If the rock is dominated by silt, then it's a siltstone. If the rock is dominated by clay, then it's a shale or a claystone. And if the rock is dominated by a mixture of clay and silt, it's simply referred to as a mudstone. So it depends on the size of the clast as to which group one of these names you will classify your rocks under. So first of all, let's start off with conglomerates and breccias. So a conglomerate or breccia is a sedimentary rock that contains gravel, pebble, or boulder-sized clast, essentially anything larger than 2 millimeters. Now, to be clear, the whole rock doesn't have to be contain clasts larger than 2 millimeters. It just has to be the majority of the rock is clasts in excess of 2 millimeters. And conglomerates and breccias are pretty simple to classify. The first thing is how angular are the clasts. If the clasts are angular, so they have lots of sharp corners, you would classify the rock as a breccia. However, if the clasts are rounded to sub-rounded, you would classify the rock as a conglomerate. So that's the first level of classification. So then we're going to look at where do the clasts come from. So are all the clasts from the same rock, or are they from different rocks? So if all the clasts in your conglomerate or breccia are all the same rock, then we refer to the conglomerate or breccia as oligomictic. That simply means all the clasts are, for instance, let's say sandstone. However, if you have a conglomerate or breccia that has clasts from multiple different sources, so you'll have multiple different rocks, then you would refer to the rock as polymictic. And then finally, is the sediment dominated by clasts or matrix? So if the rock is dominated by clasts, it's called clast supported, and if the rock is dominated by matrix, it's called matrix supported. So it's pretty foolproof. So when it comes to clast and matrix supported, I have a couple of diagrams here that kind of demonstrate the difference. So in clast supported, the vast majority of the clasts will be in direct contact with one another. In contrast, in matrix-supported conglomerates or breccias, the clasts will often be separated by matrix in between them. So you can see this particular rock here, you can see we have rounded clasts, so obviously it's going to be a conglomerate, but you can see you have lots of clasts that are separated by the matrix, so they're not in direct contact with one another. So this is going to be classified as a matrix-supported conglomerate. In contrast, when we look at this rock here, we can see the vast majority of these clasts are in direct contact with one another. This is going to be a clast-supported conglomerate. So, obviously you can see these clasts are nice and rounded. In the case of this rock, by the way, you can also see these clasts come from a lot of sources. We have these dark grey clasts, we have these kind of salt and pepper clasts, we have light grey clasts, we have clasts that are kind of, red in colour. So this is going to be a polymictic conglomerate. These clasts over here, on the other hand, are on the whole this kind of white-yellow colour. That's just quartz, and so this is a oligomictic conglomerate. Now let's look at these. These are breccias. So you can see when you look at the clasts, you can see they have these sharp corners. They're not nicely rounded. So in this case, we are going to classify this as a oligomictic breccia, because you can see the clasts only come from one source. Same for this one over here. They're all this kind of medium grey colour. This rock, on the other hand, you can see the clasts come from multiple sources. So these are going to be oligomictic. This is going to be polymictic. Now in this case, we can see that the clasts are separated by the matrix in most cases. We can see it here as well. So these examples here are both going to be matrix-supported conglomerates, compared to this sample over here, where most of the clasts are in direct contact with one another, in which case we'll classify it as a clast-supported conglomerate. Okay, so sandstones. So sandstones are sedimentary rocks that are composed of sand-sized grains, so I'm sure you're particularly shocked there. So we need to remember, of course, that sand, to a geologist, is not a description of what a sediment is made up from. It is a classification of the size of that sediment. So, if you bring me something and you say, oh, is this a sand? I'm going to measure how big the clasts are. I'm not going to worry what it's made from. I'm going to tell you, well, yes or no, it's a sand, based on how big the clasts are. So sandstones, I'm going to be honest, are on the whole pretty dull rocks. So adding extra information into the name is essential to aid field identification. So if I name a sandstone, let's say I go to hill country, I find a layer of sandstone, and I decide to describe it, put it in a map, then obviously when another geologist comes along, they're going to want to make sure they look at they're looking at the same sandstone that I looked at. And the way that we do that is by adding descriptive terms into the name that helps to give a little bit more detail. So a key point is that a sandstone must contain less than 5% clay and or silt size clasts. If it contains greater than 5%, then we're going to classify it as a Greywackes. So a sandstone has to consist, minimum of 95% sand size clasts. So the common classification scheme is this one here, and you can see that the rocks are broken up. The sandstones are broken up by the amount of quartz, the amount of feldspar, and the amount of lithic, so rock fragments that are in your sandstone. Now, we're not going to be using this particular classification scheme because it's a little bit heavy duty. We're going to focus and keep it slightly more simple, and we're going to use just two basic sandstone classifications. The first one is Arkose sandstones. So those are sandstones that have equal to or greater than 25% feldspar in them. And then we have quartz sandstones. Those are the ones that contain equal to or greater than 75% quartz. So if your sandstone is very quartz rich, it's going to be probably a quartz sandstone. If your rock is rather feldspar and quartz rich, it's probably going to be an Arkose. And then on top of that, you might add little terms, describing the color or any major textures that you can find in the rock as well. Alright, so that's been 20 minutes. So once again, pause the presentation, get up, have a walk around, go and get a glass of water, and come back in a couple of minutes. Alright, so now we're going to talk about Greywackes. So Greywackes are sediments that are, or should I say, are rocks that form from a sediment that is a mixture of both sand-sized clasts and clay and silt size clasts. So this diagram here kind of sums up what we're looking for. So if your sediment consists of sands and muds, and it has between 0 and 5%, sands mud size clasts, so it's 95% or higher sand, you're going to classify it as a sandstone. Now, if you have in excess of 5% clay and silt, you're going to fall into this field here. These are the Greywackes. Now, as soon as your sediment has greater than 50% mud in it, you are going to classify your rock as a mudstone, a mud rock. So, as long as your rock has between 5 and 50% mud in it, you're going to classify it as a Greywackes. So Greywackes are split up based on whether they are dominated by quartz, feldspar, or lithic fragments. So you can have a quartz wackes, a feldspathic wackes, or a lithic wackes. There's only 3 possible choices. It's a relatively simple classification scheme. All you're going to do is you're going to look at the rock, say, is it mostly quartz, is it mostly feldspar, or is it mostly bits of other pieces of rock? And once you know that, you'll just simply classify it based on those options. So mudstones are composed of clay and silt-sized particles. So the only way to tell the difference between a clay and silt-sized particle is, as I already described, to actually eat a very small quantity of the rock. So mudstones are often deposited in extremely low energy environments like the deep ocean or lakes or estuaries, essentially where the water's velocity goes down to nearly 0. So because on the whole mudstones are pretty dull rocks, I'm going to be honest, they are split into 2 groups. There are fissile mudstones, those are mudstones that have layering, and there are non-fissile mudstones, also referred to as massive mudstones. Those are the mudstones that do not have layering. So what we're going to do is when we name a mudstone, we'll combine the size of the class in the rock, and also we'll add in whether the rock is fissile or non-fissile. So this is the classification scheme that we would use. So if you look over here, it says the ideal size definition. So over here, if your rock consists of greater than 2/3 clay, so it feels smooth when chewed, it's going to be either a clay shale if it's fissile, or a clay stone if it's non-fissile. If it has greater than 2/3 silt, you're going to have, essentially, if it's fissile, it's going to be a silt shale. If it's non-fissile, it's going to be a silt stone. If it has between 1/3 or less than 2/3 silt, it's going to be a mud shale or a mudstone, depending whether it's fissile or non-fissile. And that's it. Once you've worked out what the class size is, essentially you have 6 possible options to choose from. It's a relatively simple classification scheme, but it works. Okay, so now we're going to go on to the carbonates. So limestones are the result of the lithification of skeletal fragments, so that's shell, carbonate particles, that's things like ooids, or carbonate directly precipitated from water. And we're going to cover that in greater detail in a few slides' time. So lithification can result in the complete breakdown of the original material. So you initially might have a layer that's made up of nothing but shells. However, during the process of lithification, those shells can break down until all you're left with is just a mass of carbonate and the original shells have been lost. So if skeletal fragments, so bits of shell, bits of bone, bits of coral, are visible in the limestone, then you would classify that limestone as fossiliferous. The fragments, of course, as I say, can be shells, carbonate particles, or carbonate clasts, and they are referred to as allochems. That's the carbonate equivalent of a clast. So the space between the clasts, or the allochems should I say, is typically filled with a carbonate cement, which holds everything together. And these carbonate cements come in 2 varieties. There's a micrite cement, or a micritic cement. That's very, very fine-grained to fine-grained carbonate, and it's pretty equigranular, so all the carbonate crystals are the same size. And then we have a sparry calcite cement that's medium to coarse-grained, and the crystals have a range of sizes. So we're just going to jump to the next slide. So you can see here, this is an example of micrite. You can see that all of this is very, very fine-grained carbonate. You know, all the clasts are exactly the same size, and they're all very, very small. In contrast, when we look at this picture here, now I've got to be honest, I looked and looked and looked, but I could not find a nice sparry calcite cement photograph anywhere. So unfortunately, this is a photograph using a microscope, but you can see in this case, this shell, here's the top half of the shell, here's the bottom half of the shell. The interior of this shell has been filled up by these very, very coarse calcite crystals. This is sparry calcite. So you have micrite, this very, very fine cement, and sparry calcite, this relatively coarse cement. There we go. So you can rarely have carbonates that are cemented by amorphous silica, but that's very, very rare. So what is micrite? So micrite forms due to the direct precipitation of carbonate onto microorganisms, or the destruction of skeletal fragments by blue-green algae. So the first way you get micrite is you have a nice warm body of water, let's say like the Florida Keys, and in that warm water you have literally billions of little photosynthesizing blue-green algae floating at the top of the ocean, doing their thing. Now over time, very, very small crystals of calcite will begin to nucleate onto the outside of these little blue-green algae. And they'll live their life, and eventually they'll die, and the carcasses will decompose. However, the little crystals of calcite that nucleated on their surface will not break down. They will simply fall to the bottom of the Florida Keys, and they'll form a layer on the seafloor. So that's one way you can form micrite. So it's buildup of very, very tiny particles directly precipitated from the seawater onto the bodies of organisms. The other way you can form micrite is if you have organisms that actually burrow into shells. So think of an oyster shell. I'm sure you guys have seen an oyster shell, and you know an oyster shell consists of layer after layer after layer of calcite. So when that oyster shell grows, between the layers, every once in a while, a little bit of organic material will get stuck. So there is a whole class of animals that make it their business to actually burrow into the shells of dead animals and try and find this organic material that's stuck between the layers of carbonate. And of course, as they're digging through the shell, they're obviously ingesting large quantities of carbonate as they go. And of course, they can't digest the carbonate, so what do? They just poop it straight out. And so that means you are also putting in very, very fine-grained particles into the water. That too can be a way of forming micrite. So micrite commonly forms in low-energy lagoons. It's also referred to as lime mud. Now it has to form in these low-energy environments, because if it was in a high-energy environment, the micrite would be stirred up, and it would probably be transported away and lost. So the term micrite comes from microcrystalline calcite. Micrite. And just to give you some example, so this is Ann's Beach in Florida. It looks, pretty unremarkable, but if you were to go to this beach and you were to take a bottle of Coke with you, if you were to pour that bottle of Coke onto the beach here, you would see that the beach would actually fizz. Because obviously the bottle of Coke is acidic, and the beach itself is made up of all these very, very fine crystals of calcite, this micrite material. And so when you put the acid onto the alkaline micrite, you obviously get a chemical reaction. So what about carbonate particles? So carbonate particles are essentially fragments of carbonate material, and in most cases they are pieces of shell. However, in some cases carbonate particles can have very distinctive modes of formation. By far and away the most common type of carbonate particle that's not just a random piece of shell is referred to as an ooid. So ooids are spherical to elliptical carbonate particles that are less than 2 millimeters in diameter. If they are greater than 2 millimeters in diameter, they are termed piezoids. So an ooid consists of a nucleus. Now that nucleus is typically maybe, a piece of shell or maybe a single grain of sand, upon which carbonate is precipitated directly from the seawater. So ooids form in very shallow warm seas. That's the reason for that is these very shallow warm seas can become what we refer to as supersaturated with carbonate. So what does supersaturated mean? Okay, so imagine you're at home and you're bored, you happen to have a glass of water and you happen to have a whole pile of salt. So you put in, a teaspoon of salt into the water, you stir it, the salt disappears, and you keep adding salt until essentially you can't dissolve any more salt in the water. The water is now saturated with respect to salt. Okay, now you're doing that with water that's at room temperature. So now if you take that water and you put it onto a hot plate and you start to heat up the glass, well, as the water in the glass gets warmer, you'll suddenly discover that you can begin to dissolve even more salt in it. So this also works with warm seawater. So in areas of the world where you have very warm seawater, like for instance the Caribbean or the Indian Ocean, you can actually dissolve more carbonate in it than if it was essentially normal seawater that you get in the, let's say, the Pacific. So this means that these very warm water environments have an excess or have more carbonate dissolved in them than they should do. They are in fact super saturated. So this means that in these warm environments, if you give the carbonate something to precipitate onto, it will very easily leave the seawater and begin to precipitate onto it. So if you just have a little piece of shell, then the carbonate will just want to naturally leave the seawater and it will begin to precipitate onto the shell and form a layer. So what happens is because you're in these nice, gentle, shallow, warm waters, the wind will obviously move the water around, producing waves, and those waves will move the ooids around. So the ooids get rolled backwards and forwards in this very lightly agitated water. Now obviously it can't be too strongly agitated, because if it's very strongly agitated, the ooids would break up. So it can only be very, very gently agitated water. So because they're constantly rolled backwards and forwards, you get layer after layer after layer of carbonate building up on the outside of the ooid. So over time the ooid gets larger and larger and larger. Essentially it's like a jawbreaker. And so we have some pictures of ooids down here. So you can see in this case, this particular ooid has a crystal of quartz, a sand crystal in the middle. These two ooids here have crystals of what appear to be calcites. These are probably pieces of shell. And this ooid here, whatever the particle in the middle of is too small to see. Now you can see in the case of these three ooids, you have lots of nice concentric bands of carbonate that have been deposited one on top of another on top of another. Now in this case, on the other hand, you can see this particular ooid is made up of lots of long elongate crystals of carbonate that are essentially radiating from a central point. So ooids aren't all uniform. They come in different forms. Some of them can be concentric, and some of them can be radiating like this one. But nevertheless, they are formed in these very carbonate-rich marine environments where they're being pushed gently backwards and forwards in shallow, warm water. So then we have the chemical carbonates. So the chemical carbonates occur in environments where we have, to begin with, seawater and fresh water that's saturated with calcium carbonate. So as we've just discussed, given the right conditions, you can supersaturate water, be it salt water or fresh water, with calcium carbonate. Now, the easiest way to do that is simply to heat the water up, but you can do it in other ways. You can increase the pressure, you can increase the salinity, you can change the pH, and that will allow you to dissolve more carbonate into the water than you would normally be able to. So in those situations as well, you end up with a supersaturated water. So then all you need to do is you need to take this supersaturated water and you simply need to give it a reason to dump the excess calcium carbonate. So the most common way of doing this is simply by taking a warm water and essentially allowing it to exit onto the surface of the earth, where it cools very, very quickly. As the water cools down, it dumps the carbonate, or should I say the excess carbonate that it has dissolved in it. You can also do the same thing by simply decreasing the pressure. As you drop the pressure, the ability of the fluid to transport carbonate is reduced, and so it starts to dump the excess carbonate. You can also do it through fluid mixing. So if you take a fluid that's rich in calcium carbonate and mix it with another fluid that is less rich in calcium carbonate, the mixture of those two fluids can in some cases be enough to cause calcium carbonate to be precipitated. And then finally, once again, if you have a supersaturated water and it comes in, well, supersaturated with respect to carbonate, and it comes in contact with organic material, it can cause the carbonate to exit solution and precipitate out. So there's lots of ways you can make this excess carbonate exit the water. So here's a couple of examples. So the first one is if you have warm and hot water, well, when that water cools down, it will deposit the carbonate and it will form travertine. So this is an area of Turkey, and you can see you have these terraces essentially, where you have water that's essentially just seeping out onto the surface. And as it seeps out onto the surface, this warm water cools down and it deposits the carbonate as it cools. Compare that to the chemical carbonates that build up from cold water, typically fresh water. That's called tufa. So this material here, this is Mono Lake in California, and these pinnacles of tufa here are being primarily formed due to the precipitation of carbonate onto organic material. So the water here is slightly supersaturated with respect to carbonate. Well, essentially the life on these pillars here is allowing some of the carbonate from the water to precipitate onto them, and it's building up layer after layer after layer of carbonate, essentially, and over time the pinnacles are getting larger and larger and larger. So then we have chemical sedimentary rocks. So these are the evaporites. So these are formed by the evaporation of water. Shock horror. So evaporites form when you have a body of water in a restricted, arid environment. So essentially what you have is you have a lake in a hot, dry area of the earth, and you are losing more water from the lake than is being put in by the rivers entering that lake. So evaporites are split into two groups depending on the type of water that is doing the evaporating. Marine evaporites form from salt water, seawater. So a good example of that would be the Mediterranean. And non-marine evaporites form from standing bodies of fresh water. That would be an example. That would be the Dead Sea, for instance. So as I said, the inflow of water into the lake or the small sea must be smaller than the volume lost to evaporation. So essentially we end up with a net loss. So marine evaporites essentially form in a pretty well-known pattern. So once 50% of the water has evaporated away, you will start seeing carbonates precipitating out directly from the seawater. Once you've gotten rid of 80% of the seawater, you will begin to see gypsum and anhydrite appearing. That's calcium sulfate. And once you've evaporated 90% of the seawater, you will begin to see halides, that's salt, beginning to precipitate. So once halite precipitation is complete, you then get a sequence of minor salts and minor sulfates being precipitated out afterwards. But on the whole, you have this very common arrangement where you'll have carbonates at the bottom, covered by gypsum, covered by halite. Now, because fresh water has a different chemistry compared to marine water, the evaporite minerals you get will be different. So in the case of a non-marine lake, halite and gypsum will dominate. So you'll have slightly less carbonate dissolved in fresh water, and so when the water begins to evaporate away, you won't get that much carbonate being deposited. Instead, you'll have gypsum and halite being the most dominant minerals. Now, you will also then get, after halite and gypsum, another class of minerals. You'll get boron minerals being precipitated. Two of the most common ones are borax, which you might know from laundry detergent, and epsomite, which you might know because it's also referred to as Epsom salts. So these borate minerals are only found in freshwater evaporites. They never occur in marine evaporites, and that's just a reflection of the different water chemistry. Freshwater is far more boron rich than marine water. So a good example of a body of water that evaporates away is Badwater Basin in Death Valley. So if there is enough snow on the surrounding mountains, either side of Death Valley, every spring when the snow begins to melt, water will come off the high ground into Death Valley and it will fill up Badwater Basin. Now, over time, that water will evaporate away and it will leave behind evaporites, and you can see the evaporites in the form of these white bands. Now, the reason it's called Badwater Basin is because as the water evaporates away, well, obviously the water that's left becomes more rich in salt, becomes more rich in calcium sulfate, and more rich in boron minerals. So that means that essentially as more and more of the water evaporates, it becomes saltier and saltier and saltier. And so people that were moving through Death Valley essentially would see this body of water, they would go there to drink it, they would find the water would be extremely salty, it would just end up making them more and more thirsty, and so essentially it would be detrimental to them. So over here we have an area marked out in red, and this area that's marked out in red covers what's referred to as the Zechstein Sea. So the Zechstein was a body of water that existed during the Permian, so between about 300 and 252 million years ago. And it was approximately, give or take, about 2/3 of the size of the Mediterranean. And it was a lot like the Mediterranean. It was a body of water in a very hot environment that got cut off from the larger ocean that normally resupplied it with water. So just imagine the Mediterranean now. If you just close the Strait of Gibraltar between Spain and Morocco, at that point the Mediterranean would be completely separated from the Atlantic, and the only sources of water coming in would be rivers like the Nile or the Danube. So the Mediterranean is a very, very hot area, and so you would lose a lot of water from the Mediterranean due to evaporation, and you would have relatively little water coming in via the rivers. So in that case, the Mediterranean would slowly begin to evaporate away, and as it began to evaporate away, it would obviously begin to deposit evaporite minerals. And exactly the same thing happened with the Zechstein Sea. It became isolated in a hot environment, the salty water began to slowly evaporate away, and it ended up depositing a layer of evaporites that's approximately, it varies in thickness, but at thickest it's about 2 kilometers in thickness. And you can see it covers areas going all the way from the United Kingdom, through Denmark, Holland, northern and central Germany, into Poland, and all the way over to Lithuania. And in Poland in particular, they do a lot of salt mining there, and they use what's called a pillar and stope method. So the stope is the room where you actually remove the salt from, and the pillars are essentially the bits of rock you leave behind to support the roofs of the stopes. So the stopes themselves, once they mined them out, well, they could refill them with waste rock, but in Poland they went for a very novel approach. Because the salt is so soft, it can be easily cut and shaped using knives. And so in their downtime, the miners that were working underground during their lunch break and their dinner breaks, they would go into these stopes and they would carve religious iconography in them. And so essentially what you have in Poland is you have several underground cathedrals, essentially in these old salt mining stopes. And if you ever get a chance to go there, they are quite spectacular. They look absolutely beautiful, and they are truly amazing. Alright, so those were sedimentary rocks. It was a nice short presentation. Unfortunately for you guys, the time saving doing this presentation is going to be mostly given over to the plate tectonics presentation, so expect a longer presentation there. Alright, so the code word for this presentation is going to be banana, and so make sure you write that down please, because you're going to need it for the quiz. So keep an eye out for the second presentation, which should hopefully be up relatively soon.